All right, today we're getting into something, well, surprisingly fascinating. We're talking about industrial energy efficiency. Yeah, I know, but stick with me. We're going to find out how the massive systems that power our world can actually be made to work a whole lot smarter.
I mean, have you ever really thought about what it takes to make, well, everything? You know, the steel in your car, the paper in the book you're reading. Pretty much every single thing you touch starts its life with a huge amount of energy. But where does that energy even come from? And maybe more importantly, where does it all go?
So, the answer is usually heat, an incredible amount of it, powering industries all over the globe. But, and this is a big but, there's a catch. At the heart of all this industry, you've got the furnace, the boiler, right? It's powerful, it's totally essential, but it turns out it's also incredibly leaky when it comes to energy. Let's dig in and find out where it's all disappearing to. And this is really the core problem right here. A huge amount of that heat we generate is just lost. Forever. I mean, a staggering portion of the energy we burn to create heat never actually does any useful work. It just vanishes, poof, into the atmosphere. So today, we're going to go on a hunt for that lost energy.
All right, so where do we even start? Well, the first place you got to look for savings is right at the beginning, with the fuel itself. Turns out what you burn is just as important as how you burn it.
So generally speaking, industries are using either liquid fuels, like oil, or solid fuels, like coal. Now, liquids, they're usually cleaner, more consistent, which makes them way easier to burn efficiently. But solids? Oh man, solids are a different beast entirely. Their quality can be all over the place, and that has a huge, huge impact.
Okay, and this is where it gets really interesting. Just look at how different the exact same type of fuel can be. The ash content in this Indian coal is almost 40%. That's stuff that just doesn't burn and can cause all sorts of problems. Now compare that to the Indonesian coal at just under 14%. And see that fixed carbon? More of that means more energy. So knowing your fuel's DNA, so to speak, is really the first step to unlocking all of its potential.
Okay, so you've picked your fuel. The next challenge is burning it perfectly. And this isn't just about, lighting a match and walking away. It's a real science, and it all comes down to three key ingredients.
They call them the 3 T's of a perfect burn. First, you need enough temperature to actually ignite the fuel and keep that fire going. Then, you need turbulence. You've got to mix the fuel and the oxygen together really well. And finally, you need enough time for that chemical reaction to fully complete. You get these 3 things right, and bam, you get the maximum amount of heat.
But, there's a really tricky balancing act here. To make sure every last bit of fuel gets burned up, you actually need a little bit of extra air. But a little is the key word. If you add too much excess air, it acts like a giant cooling fan, just grabbing all that precious heat you just made and carrying it right out the chimney. This is a major source of wasted energy.
And this image just shows it perfectly. On the left, you've got a clean, efficient fire that's turning all the fuel into useful heat. But on the right, you get incomplete combustion, and all that smoke you see, that's literally unburned fuel. It's money and energy just going up in smoke.
Okay, so we know how to make a perfect fire. But where does that fire actually do its work? Well, the answer is inside the industrial boiler.
So what is a boiler? You can basically think of it as a super strong high-tech kettle. It takes all that heat from the fire and uses it to turn water into steam. And here's a wild fact for you. When water turns into steam, it expands to about 1,600 times its original volume. That incredible expansion is what creates the immense pressure and energy needed to power turbines and run entire factories.
Now, there are 2 main designs. First up, you have the fire tube boiler. For this one, I want you to imagine a big tank of water with a bunch of super hot pipes running right through it. The heat from the gas inside those pipes transfers out into the surrounding water, and that's what turns it into steam. And then you've got the water tube boiler, which, you guessed it, just flips that design. So here, the water is inside the tubes, and the hot furnace gas is surrounding them. It's the same basic idea, get heat into water, but just a different engineering approach. You'll often see this one used for higher pressure systems.
So the boiler's #1 job is to get heat from the fire into the water. But it's not a perfect process, not by a long shot. A huge amount of energy just escapes in the hot exhaust gas that's going up the chimney. More energy is lost just turning any moisture that was in the fuel into steam. And even more just radiates off the boiler's hot surfaces, kind of like a space heater.
So when you add up all those little losses, you get a number like this one. In a pretty typical real-world example, the boiler's efficiency is only about 80.7%. Now just think about that for a second. That means for every 5 truckloads of fuel you buy, one of them is basically thrown away before the energy even leaves the boiler room.
But wait, the story doesn't end at the boiler. Not even close. What happens next is actually where some of the biggest losses can be hiding. We've made the steam, now we have to get it where it's supposed to go.
Okay, this right here is the big picture. And honestly, it's a real eye-opener. So we start with 100% of the fuel's energy, right? We immediately lose about 20% in the boiler, just like we saw. But then, look at this. We lose even more as the steam travels through the pipes. That's what they call distribution loss. And then we lose still more, where the steam is actually being used. The shocking result? Only about 35% of the original energy ever does any useful work. Almost 2/3 of it is just gone.
And here's that same breakdown, just visualized a different way. Yeah, the boiler losses are significant, but look at the losses in distribution and at the point of use. Together, they're responsible for more than half of the total energy. It's like this cascade of inefficiency, where all these small leaks along the system add up to one massive problem.
And these leaks can be so small you'd never even notice them. Let's just zoom in on one tiny little component, a flange. It's just a simple connector between two pipes. If that thing is left uninsulated, it acts like a tiny radiator, just constantly bleeding heat into the air. Over a single year, that one small part can waste 55 kilograms of fuel, all by itself.
And the solution? Well, it's often incredibly simple. Just look at the difference insulation makes. The fuel loss plummets from 55 kilograms a year down to just 1/4 of a kilogram. That's it. It's such a tiny change that results in a massive energy saving. Now, just imagine that scaled across an entire factory. Thousands of these little connections. All right, another critical component is something called a steam trap. See, as steam travels and cools down, some of it turns back into water. The steam trap's job is to let that water drain out while keeping the valuable high-energy steam in the system. But when one of them breaks, it's a total disaster. It's like having a leaky faucet, but for energy.
And you know what causes them to fail? A lot of the time, it's something as simple as dirt. A tiny bit of rust or scale can get in there and jam the valve open, letting that precious steam just pour right through, 24/7. So the really important point here is that basic maintenance, just keeping the system clean, is an incredibly powerful energy conservation tool.
And that really brings us to our final thought. We started this whole journey looking at these massive industrial furnaces, and we ended up looking at a single uninsulated pipe and a little bit of dirt. And I think it proves that energy efficiency isn't always about some giant revolutionary breakthrough. It's about the cumulative power of finding and fixing thousands of these small hidden leaks. Which really makes you wonder, doesn't it? How much hidden potential is just out there, all around us, waiting to be unlocked?